This is Katie Kimberling with TutorPUG, and this is my second video in my U-Substitution series. This is part 2, which is going to cover medium level difficulty U-Substitutions and algebraic manipulation, because not every antiderivative problem has to use U-Substitution. Sometimes problems can be manipulated using algebra, and that either lets you avoid U-Substitution or do U-Substitution a little bit more easily. So here are a quick run through some of our algebraic rules, because we'll be using those at some point. Again, the only way to become comfortable with these is to practice them multiple times until you recognize, oh, is that an algebra problem, or is that a U-Sub problem, or could it be a combination of both? So this rule right here, this is a rule of exponents, says if you have two variables that have the same base and they're being multiplied together, you write the base and you add the exponents. So for example, if you have x to the third times x to the seventh, that would be x to the 3 plus 7, which is x to the 10th. This is the same rule. It just has a different base structure. If you have e to a variable times e to a variable, you're going to write e and you're going to sum those exponent variables as long as they have the same power on them. If you've got something with an exponent divided by something else with an exponent and they have the same base, you subtract the top exponent minus the bottom exponent. So x to the 5th over x squared would be x to the 5 minus 2, which is 3. This one gets misused a lot. It's very common. If you have a variable under a radical, then you can get rid of the radical sign and the exponent on the variable becomes the numerator of the fraction exponent, and the root or index of the radical becomes the denominator. That's why the square root of x is x to the 1/2, because this is an invisible 1 and it floats to the top. And if you're taking a square root, that's an invisible 2 and it becomes the bottom. And then lastly, if we have something in a denominator with an exponent, I can move that to the top or out of the denominator, but I have to change the sign on the exponent. Something has to change. So these rules will be used frequently and in conjunction with each other, and all they can do is make the number scary. And they can combine the rules. They can use radical rules with variables in the numerator and denominator. The same rules apply. So here we have a problem. We're being asked to antiderive. That's what the integrand means. Our variable is t, and we have all kinds of nonsense here. And one of the dead giveaways is if I have multiple terms in a numerator, but only one term in a denominator, it's probably going to be simplified using algebra, because that's the direction they typically want you to go. So what I can do algebraically is I can split this up into two separate fractions, and I can write it like that. So now what I can do is this t has an exponent of 1, and this t, if I want to, I can rewrite it using this rule. Instead of writing it root t, I can write it as t to the 1/2. And same thing over here. This is 9t squared t to the 1/2 dt. Now I'll use this rule, which says, oh, I have things with exponents in the numerator and denominator, and the bases are the same. They're both t's in this case. So I can subtract the exponents. So this term is 1 minus 1/2 t to the 1 over t to the 1/2 becomes t to the 1/2 because 1 minus a half is a half. And over here, 2 minus a half becomes 3/2 or 1 1/2. Now, please note, I have not anti-derived. I haven't done any calculus yet. I've done 8th grade algebra. So I keep the integrand and the dt because I haven't done the command that's been issued yet, which is to apply an antiderivative rule. Now I have it in a form where an antiderivative rule will apply, so I'm going to do it. And when I do that, when I start applying antiderivative rules, both the integrand and the dt go away. So this is my top rule where I have a variable to a number. So we add 1 to the number, 1/2 plus 1 is 3/2. Divide by that new exponent value. And here, 3/2 plus 1, 3/2 plus 2/2 is 5/2. And I tack on my plus c. Mic drop, go home. Got my math. Dropped the integrand symbol, dropped the dt. That is the antiderivative of this problem. So let's try this one. First of all, I'm going to ask myself, can I antiderive it as is? Well, no, because I've got this product rule and I'm not allowed to use the product rule when I antiderive. So then I say, well, can I simplify it using algebra? Can I FOIL? Can I distribute? Could I simplify like we did in the earlier problem using some of these rules? And the answer again is no, because I'm not allowed to distribute into that radical sign. That means it's U-substitution. So, some rules of thumb for choosing or identifying what U is supposed to be. It's not really a choice. It's not that I get to pick what U is. It's more of an identification because the problem is telling me what U has to be. There's only one correct answer. So in this case, U is usually going to be the item with a bigger exponent. If we have 2 terms and 1 term, and one of the 2 terms is a constant, those 2 terms will be U. Typically, if I have something under a radical, that's going to be U. But really what I'm doing is I'm saying du is going to be the derivative of, in terms of variables, what I have identified as U. So in this case, U has to be t to the 4th plus 5, because I know that when I derive that, which is my step 2, this 4 will turn into a t cubed, and that gets me this guy, which is good, and this 5 will disappear, which is good because this doesn't have a constant. So I identify U, then I derive both sides. The derivative of t to the 4th is 4t cubed, the derivative of 5 is 0, and I derived this side of the equal sign with respect to t. The problem is when I'm ready to translate and do my step 3, this piece is very easy. It becomes U under the radical. But now I have to antiderive or substitute just t to the 3rd and a dt. And over here, I have a 4t to the 3rd and a dt. And I want this to look like that. I'm trying to make this be an exact translation of that. So really all I can do, it's a very simple fix. If I divide both sides of this equation by 4, that leaves t to the 3rd dt, and that translates into du over 4 or 1/4 du. So typically we put our constants or our numbers out in the front, and the du is always the caboose. It always goes at the end. Now I'm ready to antiderive. constant comes along. This is really u to the 1/2, so it's where I add 1 to that exponent. U to the 3/2 over 3/2 plus c. And then step 5, there's step 1, there's step 2, 3, 4. U is really t to the 4th plus 5 to the 3/2 over 3/2 plus c. That would be my final answer for the antiderivative of this. Happy mathing, it takes practice.